In the previous video I was talking about convolution approach or finite impulse response filter based approach to sound image of space synthesis. And so in this one I want to talk about recursive filter based approach and focus on this nice paper by John Toro called Effect Design, Reverberation and Other Filters. This is a rather old work. It's from 1997, as you can see, and the algorithm presented here is said to be one of the algorithms designed for Lexicon 224. Despite being a rather old algorithm, it's a very good starting point, and by realizing it we can see some of the problems of filters, of reverberators based on all-pass filters, and how we can overcome these problems, how we can solve them. And in itself this reverberator is very nice. It sounds interesting and can provide very interesting results. I guess in electronic music we heard a lot of it, a lot of something like it at least. Well, David Gressinger in his letter to John Toro doesn't quite say that, yeah, this is the one from this model or something. He says like it's probably one of those was designed for the reverberator, for that model. Nevertheless, let's take a look. It's an interesting thing. So we have left and right channels at the beginning, summed to mono and gain compensated. Then what we have is a pre-delay, and these text fields in this block diagram resemble the kind of the knob, yeah, the control signal in synth-def sense. The next thing that we have here is the low-pass filter, one-pole low-pass filter, same as the one I was showing in a previous video on the SC-lang part of SuperCollider. Yeah, every next output is the current input plus the previous output. Yeah, and we can see that the bandwidth parameter controls this filter from two points, one in the feedback and one the input signal. After that we get a cascade of 4 all-pass filters. Yeah, these are here since the input is mono. Input is mono here. These are here not to provide early reflection simulation. Rather, it's a method to randomize phase of the input signal and kind of start an aesthetic work on the sound image of space, because what we do here will affect what takes part later in this part called reverberation tank. Yeah. Interesting thing here is that the input diffusion 1 and input diffusion 2, yeah, this parameter controls both first and second filter, their feedback and the direct path multiplication. Yeah, so one knob controls 2 filters, and same goes here. Yeah, input diffusion 2 controls these 2 guys. The delay times the delay times are in samples, and the sample rate is said to be around 30 kilohertz. Around 30 kilohertz. So the reverberation tank. The reverberation tank consists of 2 parts, identical in structure, as you can see. The only difference is the delay times. And probably, yeah, the modulator signals, yeah. So let's take a look at this one. This all-pass filter is the same as the ones above, but we have the direct path, as you can see here, with the inverted phase, yeah, and the feedback path positive, yeah. Here it's in an opposite manner. And the next thing is that the delay time here modulates, yeah. We have an excursion parameter which is set to be 16 samples maximum. Next signal is delayed, and the delay time is rather big here compared to other delay times. As you can see, the biggest one is 378 samples here, and here we have 4,000 and half, yeah. Okay, the next thing is the same low pass filter as here. The parameter here is called damping, but it controls, this knob controls two filters at once, yeah, as well as decay diffusion here controls this guy as well, yeah. After that we have the decay, which is a feedback of this whole structure. It's present here and at the output of this half, and same goes to the left part. After that, another all-pass filter. This is identical to the ones here. Another big delay, and to the output with this decay multiplication. At the output we can see that these two parts exchange signals with each other, yeah. This is not the output of the reverberator, it's just an exchange. So this is this figure of 8 type recursion between these two parts. The output itself is a bit more complex. So these are not a left channel, right channel signal path. The left and right channel are made up out of the sum of several output taps. First goes from here, like between this all pass and this delay. The second one goes from inside of this filter, like from here, yeah, and the next one from here, and the same is taken from this part of the algorithm. So we have 6 output taps, and to the left goes all of them, and to the right all of them goes. Do I speak like a old British poet now? So the the table here represents kind of a pseudocode algorithm of calculation of output for the left and right channel. So for the left channel we take all of those 6 taps and delay every one according to corresponding delay time specified here, yeah, in this table, yeah, and we play with the polarities in the same manner as depicted here, yeah. So we can say that we take one tap delayed by this amount of signal, then we sum this tap with this delay, then subtract this tap with this delay, and so on, yeah. And the same 6 outputs go to right channel, but with different delays and different polarity switches. So that's it about this algorithm. This is the thing. If we will try to implement this in SuperCollider, first we have to keep in mind that the all-pass filters in SuperCollider are of a different type. They are not like this one. The SuperCollider all-pass filters are of this type. I found this picture, it resembles things. It's kind of some task. I just found this by the picture. I was looking for the picture of the algorithm, didn't want to draw it by hand. So I'm not sure about this impulse response. It has some error, I guess, because the amplitude shouldn't be, this amplitude shouldn't be bigger than this one, because what we have here is that this is a direct path, yeah, direct path. It gets multiplied by -g, yeah, but the second is the signal as it is, yeah. So this should be lower amplitude than this one. Yeah. So what we see here is the direct path is multiplied by -g. The next tap is this, the original sound delayed by this amount, and then we get a recursion. Yeah, and at every recursion, the signal is multiplied by g, so we get this decrease. Yeah, but I don't get why this is better. This is bigger. Sorry, bigger than this one. So this is the all pass that we have in SuperCollider. This is the first difference. Let me show you. I had some plots. This is the output of all pass n, I guess. Well, all of them will have the same all pass n, all pass l, all pass c. All of them will have the same impulse response in unmodulated delay time case. As you can see, yeah, the first one is lower amplitude, and then we get this one. Yeah, but the filters depicted in this block diagram will have this type of impulse response. You see, the signal is the polarity is alternated after 2 taps. Yeah, because we get direct sound multiplied by input diffusion, then comes the feedback multiplied twice, yeah, with the polarity switch, and the what is that, feed forward here, signal. So we have a sum of these two, yeah, and so on. If you're interested more, try to kind of calculate in your mind, and you will get like this this impulse response. So this is the first difference. The second difference between these filters and the ones we have in SuperCollider is the this input diffusion control. Here we have kind of an identical controls of the feedback. With this, with the first and second, the only difference is the delay time. But in SuperCollider, there is no direct control of this feedback parameter. The feedback parameter is calculated from the delay time and decay time parameter, which is, if we take a look at this, let's take this all pass n, yeah, we see that we have input in signal, then the maximum delay time to allocate the memory for this unit generator, and the delay time itself, actual delay time, and the decay time parameter. Now this decay time parameter is used, as well as this delay time parameter, to calculate the actual feedback. And what is that? Let's take a look at the block diagram. This G parameter, yeah. If I have 2 identical input diffusion parameters, the actual feedback here will be different. Yeah, will be different because the delay times are different. Yeah, that's another difference. So we have to keep in mind these 2 things. Yeah, it doesn't mean that we cannot use SuperCollider to realize this type of algorithm, and I will show the actual comparison between what we can do with SuperCollider tools that are present in a default distribution, and I made this type of filters in Faust, and so we will be able to compare these two guys. What else I wanted to yeah, so let's switch to them. And take a look at what we have. So let's start from this point. Yeah, from this point. This is an integrator. It also can be a one-pole filter, yeah, or you can use it just as it was in a block diagram. Yeah, input signal is multiplied by bandwidth, and then in the feedback the coefficient is 1 minus bandwidth. It will give you that filter. It will sound same as a one pole with the positive coefficient, yeah, not negative coefficient, because negative coefficient will give you high pass filter. Delay times, I just took the delay times from the block diagram itself, converted them to the 2 seconds, yeah, and use them like this with the SuperCollider's all pass filters, because they accept in the delay time in seconds. So we have 4 delay times and correspondingly 4 all pass filters, chain of 4 all pass filters. Yeah, and this is just a method to not bother with the controls. I could just put 4 all pass 4 lines with all pass, or play like that, so that first input diffusion where is that input diff? Yeah, input diff, as you can see here, input diff is an array of these 2 parameters. Yeah, they are just 2. I just took them into array, and I index it with this truncation, so that first 2 will be these guys, this guy. Yeah, for the first 2 iterations I will use this one. For the second 2 I will use this one. So next, what we have is the tank, actual tank thing. Let's take a look at the diagram again. We had low pass and 4 all passes. Yeah, low pass for all passes. Then we have this guy, which we cannot quite realize this block diagram. Yeah, but what we can do is just invert the signal before the actual filter. Before the filter, what we will get, at least the direct sound will be inverted. Yeah, direct sound will be inverted. And we have a modulator here. So here is this all pass, and I will do this phase inversion before this filter. Yeah, before this filter, but I will do that later here. Yeah, here, because I want the phase to invert every time on the feedback. Yeah, so I put it within this local out. I could also do it here, actually, like in the input specification, but let's do it like that. Why not? It just was, for some reason, just faster, I guess. The modulator here is the low frequency noise. You can use a periodic as well, but probably it's a good idea to have different phases, or maybe a bit different frequencies. Yeah, and of course different amount of the modulation. The next thing, I have the delay C here. What I want to say here is that you can see, like, okay, here I use L, yeah, the linear interpolation, and here I use cubic interpolation. Well, what's the sense? I don't even modulate the delay time. The thing is, to my ear, they sound different. I don't know. So I was just playing with different variations of filters, and kind of this seemed sounding better than others. I don't quite remember, because I made it like about well, I was playing with this model several years ago, but this actual one I made it 3 weeks ago, or even 4 weeks ago. I wanted to make this thing faster, but stuck with another project of mine, so delayed that stuff a little. But the thing is, when I was playing with it, different filters appeared to me as sounding differently, and this is not the first time that I see that in more complex structures. Actual this interpolation plays an aesthetical role even without modulation of the delay time. Okay, next thing is low pass again. Next, another all pass, yeah, and the delay time again. I compensate for the overall delay time to one control block, because then after this point the signal goes here, which is a local out, yeah, and recursion inside of the synth-def gives us one control block delay, additional delay. Another part, which is the right part here, yeah, designed the same way, designed in the same way, and you can see that I specify this n out 1, n out 2, n out 3, yeah, and same goes here, n out 4, n out 5, n out 6 variables. I specified them so that I will take them later here and form a left and right channel using the mix unit generator, mix, playing with their polarities here, yeah, and using the delay times which I calculated here. I just placed it as it is, and these are the original ones, and this is the actual sampling rate that was on paper. The thing is, another thing, we cannot take the output from the inside of the filter here, yeah, that's what it is. But let's just take the signal before it. Let's just take this output of this dumping, yeah, of this decay, yeah, decay, which is here, and out 2. This is just the output of integrator, yeah, multiplied by the decay. Integrator multiplied by the decay, yeah. So I assign this to variable, and this is the signal I take. So I take signal from here, and out 1, output of this all pass, yeah. I take output from here, and I take output from all pass L, yeah, the last one, from this all pass filter, and same goes for this part. So that's how I was able to do that with the SuperCollider based unit generators. But I also, just for comparison and for the sake of fun and out of curiosity, I made the filters that behave like the ones that behave in the same way as these ones, yeah. So what I made is, let me show it. This is the block diagram of the filter that, well, should behave in the same manner as this one. We have an input signal X, yeah. It goes to the output and gets multiplied by this A slider here, yeah. In SuperCollider this will appear as just the input called A, yeah, the same thing that we have here, yeah, this multiplication. The same signal goes to the feedback, where it gets delayed by the delay parameter, and this delay signal goes straight to the output, yeah. So this is this path, yeah, and here it's summed, it gets summed to the direct path as well as this feedback path, yeah. And this feedback path goes from here, it gets multiplied by A again, but this time it's 0 minus A, which means if this is positive, this will be negative, yeah. If this is negative, this will be positive, yeah. And the range for this slider, let's say, or the effective range of the SuperCollider input is from -1 to 1. This is important to understand, because if you actually can provide the value like -2, yeah, bigger than this range, yeah, but it will not be effective. Like, it will be, the value will be clipped, I guess. Well, you won't hear it, yeah, it will be clipped probably. Oh, what? Okay, now, yeah, and another one, because here what that -1 +1 for this parameter allows me is to switch the polarities here, yeah. I can switch the polarities here, yeah, with this range of from -1 to 1, yeah. But another thing is this guy. This guy needs two outputs, one that goes to the output of the reverberator and one that goes further. Yeah, so I designed another one, and this is the same as the previous one. It's called bipolar A two outs, and here we have another out that goes from here and goes straight to the output. So this filter will have two outputs. Okay. So what I do here, you are not the one, this is the one. This is the one, it's called Datoro DG Reverb 0. This one has Faust all pass 2 comps. Yeah, Faust all pass 2 comps. I didn't show it with Faust, just don't want to waste time. It's same as this one, but just the range of the A parameter is fixed from 0 to 1. Yeah, I could use this one, just was lazy a bit because this one was made first. So I have this here instead of all pass L. This one with the inverted polarity here, and this one with two outs here, and I index its out here, here, yeah, here. So the 0 goes to the output, yeah, and out 3 at 0 goes to the recursive, yeah, to the recursion. So the n out 3 at 0 goes to the recursion, yeah, but n out 3 at 1, where is that 1? Yeah, at 1 goes to the output of the reverberator, yeah. And same happens for n out 6, yeah, the other part of this reverberation tank. So what? Let's take a look at how they sound. Yeah, this is the SuperCollider unit generator based one. Does it work? Oh, what is that? What is that? Oh, I hear my own voice. Do I want to have this? Oh, no, I didn't want to do this. Actually, what I wanted to do. Oh, let me listen to my voice. No, I will ruin all the shit. I want to make some connections. Yeah, I want to make some connections here. Where's that? Output from what? Also jack capture goes where? This is a simple string recorder. No, not this thing. This SuperCollider out 1 goes to analyzers. And what else? Hardware. Other hardware. Other. We have system connected to SuperCollider. Yeah. And now that's it. That's what I wanted to do. Okay, so we have this guy. This is SuperCollider unit generator based one. Yeah, I made the controls especially for input diffusion and decay diffusion as close as possible to those that were specified in paper. Yeah, taking into account that, well, they will not be identical, they will not be same here and here, because I still use input diffusion parameter just for the decay time. Yeah, for the decay time of these filters. Yeah, here, where is that? Here you can see decay time equals decay diff 1, and same goes here. Yeah, but and here is another one. Here is this one. Here's this one with my filters. Yeah, filters that I made in Faust. And here the parameters are just this input diffusion and decay diffusion are just as was specified in the paper, in this paper. Well, you can find them later in this text. Other than that, these are identical with the parameters for damping and dry wet and so on. They're a bit different, but well, I cannot say for sure after playing with them a little. Of course I played with them a little. I'm not sure if which one is better. Oh, sorry. We can play with the input bandwidth, input bandwidth, as well as we can make the reverberation tail lose high frequency energy with time, And in my own view, this reverberator is like just designed for the high reverberation time, Okay. Окей. Что-то я увлекся. Yeah, let's go back. I wanted to talk about some problems of these recursive based filter structures. The recursive filter based structures. I wanted to take a look into some problems. Let's take a look at those problems. These are same for both type of filters. What are they? Let's remove this decay time or the recursion of the whole tank structure, and take a listen at the all pass filters themselves. Hear that? Now, what is that? The metal, Where does this metal come from? The name itself, all pass, means that it only affects the phases, but not the amplitudes, But the thing is, the tap themselves with a certain interval generate the pitched signal with the periodic waveform, and correspondingly harmonic spectrum. Yeah, this is an all pass N. Hear that? That's the thing that we use to make a reverberator. And same goes for another type. Same thing, yeah. So in the problem itself is inherited from the basic element that we use to make this reverberator. First thing that we can do in order to minimize this harmonic output from the all-pass filter, of course, is to diminish the overall decay time. Yeah, the decay time of every filter. If we make them smaller, let's listen again. Okay. By decreasing the diffusion or the feedback of the filter, we get less of that metallic sound, yeah, but we lose the diffusion. The reverberation becomes more echo-like, yeah, and doesn't sound as room or the hall and so on. So this can be told like this can be called a kind of a fundamental problem of this approach. We have what is that? Echo density versus resonance density. So if we increase the diffusion, echo diffusion, we get more elements, yeah, more echoes in the impulse response. So echo density grows, yeah, but at the same time we get more resonances, yeah. We want to get more echoes but less single resonances in the spectrum. Yeah. And the last thing is this input bandwidth. By limiting the reverberation input itself, I will get less of those values, less of the spectral part of the signal that will contribute to the periodicity of the filter outputs, yeah, by limiting this bandwidth. Yeah, and the next, of course, by adding the decay and removing the damping first, yeah. And now introducing the direct sound. And this is more or less good, yeah. And you can hear this echo-like sound with this SuperCollider filter based variant more obviously, yeah, than with the previous one. And it comes from these two delays, yeah, or these 4 delays, which are, as you remember, are much bigger than all other delays. The thing is, when we increase the decay, the metallic quality is not that big problem anymore, because it gets masked by the later sound, yeah. Well, more or less, yeah. And when we will later make the mix, it's not that big problem. Maybe it's even more interesting in some cases, yeah. But in my opinion, these big delay times could be controlled by some scaling factor, yeah, some additional control. So let's now take this structure as it was and make a more elaborated reverberator, but following the principles from the original one. And I will use this SuperCollider based one, yeah, SuperCollider unit generators based one. You can make the one using these filters. I will include the files DSP code for these filters as well if you want to play with them. But this one is kind of faster to get, yeah, because you can just launch it in your SuperCollider installation. And let's take a look at what I would add here. I made just little additions. You can make much more. The first thing that we can do, and it's another thing of solving the problem of echo density versus resonance density, is just to increase the number of all-pass filters. This is also a method. Yeah, here we have 4 of them. You can put more. You can put 8, for example, and that will make things much better. Remember, this design is probably like 40 years old, yeah, and the calculational capabilities at that time were very low, yeah, and today it's just not a problem at all. So this is the first thing. I leave it as it is, but you can increase, of course. Second thing, you can use all pass what is not N but C or L, yeah, and modulate the delay lines, yeah. Delay lines modulation is another method to overcome that metallic sound problem, yeah, because you start to randomize the resonating modes, and the resonances are not that obvious now, yeah, they always floating a little, so that also can be a nice feature, nice effect, if put in the right context, right artistic context. The second thing I would add is this tank delay scale, yeah, T-del scale. I put it on these longest delay times, yeah, so that I would be able to play with that as well, because that's kind of a characteristic of the sound image. Why not affect it? And what I did here, I just added the delay line modulation to all of these guys in the tank, just for fun, why not? And probably the last modification that I added here is this high pass frequency filter, yeah, so that in the tank I'm not only losing high frequency but low frequencies as well. Oh yeah. So that's it about the reverberator itself. As I told before, the diagram itself doesn't include the method to generate early reflections, yeah, naturalistically. So I just take the reflector from the previous videos. I control it here totally by the seed number. All the parameters except for low pass, high pass are randomized, and I control how much I want of early reflections, the direct sound and tail, and yeah, and also the input to the reverberator goes as the mix between direct sound and early reflections, yeah, so I can balance between them. For that I use this Lean X Fade 2 unit generator, very convenient one. Let's take a look at what we can do with the same that drums input. I use drums in this video because drums show that metallic problem better than others, because with some sound sources you won't even probably notice a lot of times this metallicness. It becomes more apparent when the input signal is percussive, yeah, has fast attack and decay, yeah. Okay. So we have a direct sound, early reflections, direct sound, early reflections. Somewhere here, yeah. and the tail. What we have for this tail signal, we have all the previous parameters like almost as they were before. Decay is a bit bigger, let's make it smaller for now. We have a delay time scale, yeah. More room-like sound, yeah, we get more room-like sound, so we benefit from this parameter. The modulator. This modulator controls, this mod parameter controls the rate of modulation as well as the depth of modulation. Yeah. Hear that? And the high pass filter for the tank. Yeah, that's about the reverberator. Now the input to reverberator, as I said, is the mix between the direct sound and a bit phasey sound, yeah, early reflections. Yeah, can give phasey sound sometimes. I was talking about that in a previous video. But as you can see, we can change the aesthetics dramatically by making the balance, by balancing between the two. Yeah. So let's add. Where is that? Where is that? Where is that? Yeah. Let's play with the. This dry wet here is I just left it. I don't remember why. I should clear this synth before executing. It was just here, but I don't actually use this parameter. Dry wet, where is that? Oh, it was in the, yeah, it was in the preset. Well, this set command, yeah. But in def, if you use in def, like this one, yeah, in def. You can set all the parameters with one command, .set, yeah. And the thing is, when you play with this GUI, which is provided here by ndef mixer command, this one, yeah, ndef mixer takes server as argument, yeah. You can then push this duck button, and it will give you your reverberator the whole source code which you sent to it. And the set, the last set, like the positions of all those knobs, yeah, very convenient if you prototype something and you want to keep some presets, let's say, yeah. Every string like this, every line like this can be considered as a preset. So the one thing that I would add to this reverberator, because as to my ear, it sounds, the most beautiful sound you get out of it when you increase this decay parameter, when you increase the feedback of the tank, yeah. What I would add is the gate after the signal, yeah. I will not do it here because gate is in itself is probably a bit long talk, yeah. In some other videos I will talk about the gates and compressors and all that, but this is the thing that you probably heard a lot in music, especially in 90s. I remember the music of those days, like especially hip hop and what was back in the days, the trip hop and all that stuff. Yeah, Bristol sound and all that. They had that gates on a longer reverberators all the time, and because it sounds beautiful. Yeah, and this type of structure, I guess that the algorithms that they were using are very much alike. Yeah, you can use this to create this type of effects beautifully. The overall thing to tell about, well, the general thing. Okay, one important thing to tell about this reverberator is that since it takes a mono input, yeah, we have to consider it as kind of a unit per input. Yeah, what is that? Am I inventing terms on the fly? What I mean is that it's not quite suitable to be used as one reverberator for several sources, because what natural space does, for every source in a different point of the natural space, it gives different impulse response. Yeah, and if you remember the previous video when I was using stereo convolution, yeah, I had two impulse responses. Yeah, so the left signal was getting one impulse response, left input signal, and right input signal was getting another impulse response. Yeah. So by panning the sound source, the input signal, we were also panning the sound image of space, and we were changing it because we were changing the balance between two convolved signals, every one with its own impulse response. That's a realistic approach, yeah. But this one is not, because it synthesizes the stereo input from the mono signal, yeah, so-called pseudo stereo signal, yeah, synthetic stereo signal, and so on. So it doesn't follow the stereophony of the input signal, yeah, and that means that you will kind of get non-naturalistic sound image of space if you use one unit with different scents with different scents. Yeah, the stereo reverberator is better for this type of task. So this is cool, but another thing is that actually a lot of sound engineers prefer this type of approach. Why? Because it gives you kind of better. It gives you. Yeah, because it gives you better control. It gives you better control. Yeah. So this is a kind of a dilemma. Yeah, dilemma. In Russian, it's dilemma. It's a dilemma because we have to we want to have the control, at the same time we want to have the naturalness. Yeah, but you don't get that naturalness even in a natural conditions. Like you imagine, I don't remember if I was talking about that in a previous video, but the most classic way to record let's say an orchestra. Yeah, if we record an orchestra, what we have is let's say XY for the naturalistic recording, XY, two pair of the pair of identical microphones. One looks this side, another one looks this side. Yeah, cardioid directivity usually. This is kind of the early reflection microphone pair. It takes the early picture of what we have. Then we have some spot microphones, which are taking the direct sounds from the instruments. Yeah, and the one reverberation pair, usually AB or maybe XY as well, but AB probably will be better because it allows you to get the wider sound image. Yeah, so at some point in the hall where you record the ensemble, you put these facing like to the other side of musicians. Yeah, it's not looking to the musicians but looks to the wall, for example. Yeah, so we have a pair of these microphones, yeah, and that's all you have. That's the way you get everything done, and if you done everything correctly, you get a beautiful sound image. Beautiful, yeah. This is the naturalistic, at the same time very impressionistic, yeah, impressionism, yeah, impressionistic approach to sound image creation. So same goes with the reverberation, with the reverberators. If the reverberator imitates the natural space, good, that's the way you go if you want to get the naturalistic sound image. But if you want to get control, you go this way, yeah. You have a unit per input, yeah. With natural instruments, almost never possible. I mean, it's possible, okay, but you take the quartet, they play Shostakovich, for example, and you say, okay, now the first violin plays the whole part, I don't want to hear anyone else, we will record its signal, yeah. Not going to happen. Okay. This one is not naturalistic reverberation. It can sound natural, yeah. It can sound natural. It can sound very interesting, yeah. But I just pointed like what it lacks. In the next video, I will talk about more about kind of what is that lower level methods of solving that metallic sound problem, that periodicity and the reverberation impulse response with recursive filters problem. I will talk about other methods. Again, I will do some Faust stuff. And if you want to use the filters that I introduced here, there is a small video on my reflector plugin that I introduced previously. You can watch it. It's not a long time, like about 10 minutes long. Step by step, I explained how to install them using online compiler. And yeah, the last thing I wanted to point, the last thing I wanted to do is to take a listen how this guy sounds with synthetic signal, with the synthetic input, with this very small example. With this very small example, what we have here, this is a sound source, yeah, is a comp filter. It's a relative of all-pass filter, yeah. The structure is almost the same, but it's a bit all-pass filter is a little bit more complicated than comp filter. Comp filter is simpler, and it's a filter that has this periodicity more periodicity present in a more obvious way in its sound output, and that's one of the reasons why it's a good candidate to be used as a periodic signal synthesizer, yeah. The algorithm is called Karplus-Strong by the surnames of the researchers who describe this algorithm, yeah. This is the simplest way, the simplest variant of this algorithm. So let's use this guy for the input and take a listen at how it sounds with this reverberator. And on this, I'm saying goodbye and hope that this will be useful in your sound design.